do this particular question. I really don't. But I'm afraid if I don't do this particular question, I won't catch the people who are looking. What I mean by that is there's an example that I usually do right at the very beginning of AP1, and then even in this class, I usually do it right at the very beginning, and I didn't this year, thinking, oh, I don't have to do that one. And then as I thought about it, I realized, yeah, I say that, and then the moment I believe that to be true, one of you guys is going to make a liar out of me. So here it is. We want to talk about the elevator question. Shut up. Some of you need to see it. If you don't remember the elevator question, I don't care. I want you to imagine that I have an elevator and an occupant whose combined mass is 300 kilograms. The elevator is going to accelerate upwards with an acceleration of 2 meters per second squared. It'll do that until it reaches its cruising speed of 2 meters per second, where it will cruise at a constant speed of 2 meters per second for several seconds until it reaches the floor where it's going to stop. When it reaches the floor where it's going to stop, it accelerates downwards with an acceleration of 3 meters per second squared. Please tell me the tension in the cable during each portion of the elevator's motion. The tension in the cable for each portion of the elevator's motion. I have 3 question marks. I have 24 kids. I think I can find 3 volunteers. Well, actually, no. Let's go with victims. It's October. Okay, upwards is positive. So, step 1, is this a first law or second law problem? Can I tell? I can tell. I was given an acceleration. Net force is ma. So I'm going to start from the standpoint that net force equals ma. There are 2 forces acting in the beginning. There's a tension force and there's the weight. I specifically making the tension bigger than the weight. Why? Because it's going up. More than going up, it's accelerating upwards. So the weight is 3,000. And the tension is unknown. But it accelerates upwards at 2 meters per second squared, so tension minus 3,000 has to equal 300 times 2. Is there a question? All right. So tension equals 3,600. We good? We're following the steps. Now, I know just from looking at it that the tension in the next 2 cases is going to have to get less and less. In the next case, the tension has to just match the weight. The velocity is constant. The acceleration is 0. Therefore, it's not accelerating. And then the next case, the acceleration is downwards. But the weight doesn't change. In all of these, the weight is the same. So if I want to accelerate downwards and the weight is the same, I need to reduce the tension upwards so that it is less than the weight. But the downwards arrow in all of these should be the same size for all of them, since the weight never changed. So I don't think I have to talk too much about the center one, do I? I mean, I'll be happy to. But let's definitely talk about the one on the right, because I think there's some students who still have difficulty with it. And I believe the net force is still going to equal ma because the system is accelerating. But I've still chosen that upwards is positive. So tension minus 3,000 has to equal 300 times negative 3. The net force has to be downwards, and it has to be negative then, which is going to give me T equals 2,100 newtons. No, it's okay. You're right. And there's little mistakes too, but one of the major mistakes students makes is forgetting that once you have set your direction for your problem, you need to consistently follow that direction. You need to make sure you're considering what direction things are happening and what direction forces are occurring in. It also brings out other little problems. The idea that you do need to consider all the forces acting in a system and that the direction of the acceleration plays a prominent role in determining how forces respond. We saw, I know exactly where this error comes from, and I know exactly where this error comes from. So be aware, you are not alone. I see these all the time. I just don't want to anymore. Next. All right, this one is a little more in line with what we talked about last week. Earlier this week. It at least has to do with friction. I want you to imagine I have a box that is kind of flung onto a surface whose coefficient of sliding friction is unknown. The box has a mass of 2 kilograms and has an initial velocity of 4 meters per second. It slides 20 meters until it comes to rest. What's the coefficient of kinetic friction? Let's establish the direction for this problem before we get started. So, what do you think? This way to the left to be positive? Is that okay with you guys? Because that's going to dictate how I set up my coordinate system. This goes against what I said as your priority for establishing direction, which should be in the direction of the acceleration. What is the direction of the acceleration in this case? The acceleration is not to the left. The acceleration is to the right. The box is moving to the left, but it's slowing down, so the acceleration is to the right. If I want to stop this box from moving, what direction would I have to push on it? To the right. So the frictional force must be to the right. So when I draw this, and I wouldn't have gone through that if I hadn't seen it drawn wrong on a lot of papers yesterday. When I draw this, I'm going to have weight downwards, 20, normal force upwards, and friction to the right. Those are the forces acting on the box. Now, I need to establish my coordinate system, and I would encourage you to establish it in a way that makes sense. And it's not lost on me that the box is moving to the left, but I told you guys that when you're establishing this, that doesn't look like a right angle too good, but I'm going to have to leave it like that, that you should choose as your priority the direction of the acceleration, which would be to the right. If I make this the positive x direction, then you do understand that later on in the problem, I need to make that negative and that negative. This is where we start running into trouble because we need to connect the parts of this problem together. And I don't think you guys do that. And although that's not a deal breaker, I do find that if students aren't connecting the parts of the problem together, they tend to make mistakes with their negative signs or just ignore them completely, which you can do at your own peril. So I'm going to say, to make this problem a little bit more consistent, let's make the direction of motion the positive x direction and up the positive y direction. Now, in doing it that way, I establish that the net force in the y direction, still being 0 because it's balanced up and down, is going to tell me that the normal force equals mg. That's not a surprise. The normal force equals 20 newtons. However, in the x direction, my net force is going to equal ma, but my friction is in the negative direction, so negative F equals ma. Now, can't solve this unless I know what A is, and I don't have A. But truthfully, I do. I have all the pieces that I need to get the acceleration. I know the final velocity is 0, the initial velocity is 4, and I know that the displacement is 20, which means I have everything I need to figure out what the acceleration is going to be. And when I do that, I find the acceleration is negative. 16 over 40. So is that what? Is that 0.004?
No, it's just 0.4.
Just 0.4. Thanks. But it is negative, and I think it's appropriate that we remind ourselves that it's negative, because when we put it in over here, this will produce an answer for the frictional force that is positive, giving us the value of the frictional force, which I guess is 0.8. It's not a big deal that we be so careful with the negative signs here in this part of the problem. But I did have people asking me, is the coefficient of friction negative yesterday? And the answer is no, it can't be. The coefficient of friction can't be negative. By definition, it can't. The coefficient of friction is the ratio of the frictional force to the normal force. So it's not going to be negative. In fact, this isn't a vector equation. In fact, the vector stuff has been stripped off purposefully. So I don't want people to just be blindly throwing stuff in there. I guess this is what's 0.04. That's how this problem is done. Questions? All right. I'd like you to tell me the shortest distance the truck can stop in without having the box slide forward in the truck. In doing this, you may have those variables in your answer and any fundamental constants you would like. For example, you might want to have, say, G in your answer. That's fine. But that's all that can be in your answer. So I want to know delta x in terms of these variables, and I want you to tell me the shortest distance it can stop in without the box sliding. Again, two goals: expressions as an answer and how to deal with inequalities. So I'll let you guys do that. Talk it out, because I intend to pick on at least, well, one of you, probably whoever's been absent the most. So you guys at home, would you like a breakout group so you can talk to somebody? It's all up to you. A couple people say yeah, so all right. If you don't feel like jumping in there, don't, but here it goes. You're going to lose your access to the picture in just a minute. So there you go.
Mr. Shelton,
Yeah.
is the truck the square in the front and the rectangle?
Yes, the truck is the square in the front and the rectangle.
Okay, thank you.
You're welcome. Apparently my drawings are garbage there. That's the truck. You tell me about it, I'll write it down.
So you want me to go through the steps to get it?
Sure, every little bit.
All right. So using the sum of the forces equals mass and acceleration, and knowing that the frictional force is less than the static or coefficient of friction of static friction times the normal force, we got an equation for the acceleration, which is v naught squared over 2 delta x.
You guys at home, can you hear Matt when he talks? All right, so
No.
let me repeat a little bit about what he said, because I don't know if you guys can hear him or not. So basically he said that the first thing he did was he recognized that the net force equals ma. And then after recognizing that, he said that he knew the frictional force was going to be less than or equal to mu times the normal force. And then he said that they found out an expression for the acceleration equal to v naught squared over, what was that?
Over 2 delta x.
2 delta x. I think that's as far as he's gotten so far. Let's stop there. Any questions about this? All right. He has made at least one assumption that I think we should all bear out, that apparently the delta x was positive and v naught was negative. Because I'm pretty sure that if you work this out and you let v naught be positive, this would be negative v naught squared. Is that true?
It has to be because of acceleration.
because 0 minus v naught squared equals 2a delta x. So there'd be an explicit negative sign here in the acceleration to indicate that's the opposite direction of the direction of motion. The thing that's dictating the direction here is a and delta x. They're dictating direction, not the velocity, because the velocity is squared. But if delta x is forwards, this is indicating that the acceleration has to be backwards. Does that make sense? Look, guys, I'm going to ask that question again, and I want an answer, actually. If we looked at the original function that brought us here, that's the original function. When you solve that for a, you get an explicit negative sign if you set this equal to 0. The reason I'm bringing this up is because it's telling you that your acceleration must be in the opposite direction of the only vector left, and that's delta x. Because v is squared, its vector information is gone. I need you guys to be intelligent physics students here and recognize that direction is built into all of this. And you need to be careful about direction. It can come up against you sometimes. Right now, I'm choosing examples where the directions are obvious. But if it's less obvious than this, and the question that comes down to what is the direction in which that occurs, you need to have some confidence that you understand how to derive direction when it's not obvious. So, I'm going to leave that negative sign in there if that's okay, Matt. All right, move on, because I know where you're going with this.
Because the forces are in balance in the situation, well, yeah, but it's accelerating. The vertical components are going to be 0. So the frictional force is the only thing that's going to be on the unbalanced forces. So that.
Okay, let me make sure you're going pretty fast. So it sounds like you've made a free body diagram that looks like this. And you have indicated there's only one force, friction, acting on the box. What direction does that force act, left or right? The force friction acts to the left. That's based on this diagram. Yes, that would have to be true. And you've gone a little bit further and said that the net force in the y direction is going to be 0, and the net force in the x direction is going to be ma. So that suggests that you have come up with a coordinate system that's aligned in that way. So something like that. And what have you set for positive and negative here?
So y positive up, and then for x it would have to be right to the right.
It doesn't matter. Just be, I would say that you've already chosen that because it seems like the variables you had in your motion equations were positive in that direction. But let's go with that. Okay, so what do I do now?
So the only force acting in x direction is going to be the frictional force. So I plugged in, because you have the inequality in there. For now, I was just not worrying about the inequality, and just plugging in the coefficient of friction times the normal force, which is also equal to mg, into one side.
Okay, so just, you guys can't hear that. He is just assuming that this is an equal sign instead of inequality, not worrying about that right now, and doing a direct substitution of mu s times n in for friction here, and setting that equal to ma. And I think he went even further and said that he didn't use n here, but he used mg. So that's a lot of steps all at once. For my people who are new, and I know Matt's going to get the right answer from doing this, but I'm going to slow him down, and I'm going to go a little bit slower for the folks who are new to this. In the y direction, I have normal minus mg, and that equals 0. Y direction, net force equals 0, so I can balance it out, and that's going to give me that the normal equals mg. In the x direction, yeah, I'm going to say friction equals ma, and I'll put a negative sign because it points in a negative direction. Here's where I'm going to change what Matt's doing, and this is where you guys who don't really know how to deal with the inequalities should listen up. I think it's important that you guys understand how to deal with inequalities, because those are threshold questions, and there's a lot of threshold questions in physics. And it's a little bit harder at the end to try and figure out the threshold portion of the problem than it is if you carry the threshold with you in the question. And if you don't understand what I mean by that is the threshold is here. That's where the inequality is. If you want to preserve the inequality, you need to substitute into this function. That's what you must do. So instead of substituting out of that function, which is what I think a lot of you did, by replacing friction with mu times the normal force, I want you to substitute into that function. So for friction, I'm going to say friction is minus ma. And that's got to be less than equal to mu times s times the normal force. I'm going to substitute into that mg. So what I've done is I've taken friction and substituted into the inequality for friction, and I've taken normal force and substituted into the same equation for normal force. This preserves the direction of the inequality and allows you to know what is actually less than or equal to what else. Sometimes it's harder to figure out where the threshold goes at the end of the question. So putting it in there now is helpful. I am going to have to make this substitution for the acceleration, because that can't be in my answer. So minus m times negative v naught squared over 2 delta x is less than equal to mu s times mg. And now you can solve for delta x. And because you're solving for it here, the inequality has been preserved. So you're going to get an answer that has your inequality in it, as you would expect. So cancel out the m's, cancel out the negative signs, and now I can get delta x by itself, and I get delta x greater than equal to v naught squared over 2 mu s times g. And I'm doing all of my algebra in one step. I hope you guys, don't need me to tease that out, but if you do need me to tease that out, I can. And you should check and see if your units work. That's what I was saying to do before. The top of this is meters squared per second squared, divided by the bottom of this. 2 and mu do not have units, but g is meters per second squared. So if I cancel all that out, I'm left with meters. That gives me great confidence that my algebra was done correctly. In addition to that, my threshold is left in place. It says that delta x can be greater than this, but it has a threshold where it stops. It can't be anything smaller than that. The last part of this is the reason why expressions are important is it tells you what matters. Does the mass matter here? So it doesn't matter how big that box was. So if I have big boxes and small boxes, but they're all made out of the same material, they're all going to behave the same way because the mass doesn't matter. On the other hand, whatever speed the truck's going at when they hit the brakes, that matters. It matters the most because it's squared. There's nothing else you can really adjust. You can try and make the static friction bigger, but it doesn't really let you start your stop much faster. Because if you double the coefficient of friction, you only make your stopping distance half as far. But if you double your speed, you have to increase that distance by a factor of 4. So those types of discussions are what you need to be able to have with an expression, and that's why we get expressions for our answers. Again, I'm going to apply a force. That's the angle. I'm going to apply in such a way that the box, I hope, stays in place against the wall because there's a coefficient of static friction of mu s. I want to know how hard you can push on the box and how soft you can push on the box without the box moving against the wall. There are only a few minutes left, 10 minutes or so you don't have much time to really bat this one around. So give it a shot. All right, so I think everybody's back. Yeah?
I was just gonna say you're muted, but you came back on.
Okay. Hey guys, let's get started now real quick. So I brought everybody back in. So the biggest issue here, aside from having to deal with the inequality, is also the fact that we have to figure out what direction does friction act. If I don't push hard enough, the box is going to slide down the wall. If I push too hard, the box is going to slide up the wall. That suggests there's actually two different problems here. There's the problem where the box can slide down the wall. And there's the possibility that I could push too hard and the box will slide up the wall. So when I do that, I mean, the angle's not any different. Still got theta, still have mg, but now the friction's going to have to be this way to prevent the box from sliding up the wall. So these are the two cases of my problem. And it's not too hard at this point once you realize that's what you have to do. I will have to set up a coordinate system, and I think in this case it doesn't really matter what coordinate system I use as long as, you know, I'm being consistent about my positives and negatives. Positives and negatives. I would encourage you to realize that you can probably use almost everything from one solution for the other solution. So I'm going to just do this one time and then see if I can kind of convince you that I don't have to really do very much work to massage it to fit the other side. So based on what I have here, only one of the forces has to be resolved in the components, and that's this one. And I'll have F cosine theta here, and I'm going to have F sine theta there. So I would never put the components on the actual free body diagram that you have to turn in, but we're just trying to come up with a solution to this problem. So now that we have all the pieces in place, net force equals 0. So if I look at that in the x direction, I would get F sine theta plus friction. What am I saying? That's the y direction. Silly Shelton. F sine theta plus friction minus mg equals 0. And in the x direction, I'm going to have F cosine theta. Well, I made that's negative, plus normal force equals 0. I don't know why I'm doing it like that. It's probably because I'm all alone here in my classroom because everybody left because they called seniors, and I'm continuing the problem. See? They called seniors and they all left. Then the bell rang. So I'll remind you that ultimately friction has to be less than or equal to mu times the normal force. So what am I doing? I am trying to substitute into this function. So to do that, I need to take these two equations that I have and figure out that on this side, I can write normal force as F cosine theta. And on this other side, I can solve for friction and get friction equals mg minus F sine theta. All right? Any question about that, I hope? Hope there's none. So now it's substituting. So let's do that. Move that all up there and finish my substitution. So I'm going to get mg minus F sine theta less than equal to F cosine theta. Now I want F, so I need to get the terms with F to the same side. But it seems to me I forgot something. Ah, yes. Forgot to make sure I left my mu in there. I got rid of it. There, mu F cosine theta. But again, I want to get these terms on the same side because they both have the force in it, and I'm trying to figure out the force. So mg It has to be less than equal to f sine theta plus mu f cosine theta. I'm going to factor out the f's. And now I need to solve for f. And here's where I get the one of the answers. There. Since I wrote f on the other side, I flipped the sign over. And this says that my force has to be greater than or equal to mg over sine theta plus mu cosine theta. Now, that's just one of my answers. But do I really have to change very much to get the other answer? Let's put this away for a minute, kind of leave him up there, and consider what was here. If I look at what has to change in order to go from this to this, all that has to change is one sign in one place. There. How does this affect the problem? Well, it would mean that this would still be negative. What else did it mean? Well, it means that if I made this positive, this would be negative and this would be positive. Well, let's trace that through the rest of the problem, shall we? Put that away. Bring this back. So, again, not a big difference, but a difference still. Hold on. Putting this over here so we've got it. So the first thing I'll notice is that when I do my substitution into friction, I'm not going to have mg minus f sine theta. I'm going to have f sine theta minus mg. That's from here. But that's going to still be less than equal to mu f cosine theta. So this is what I had before, this is what I have now. I'm still just solving for f, so I'm going to move this term over there and get f sine theta is less than equal, minus mu f cosine theta is less than equal to mg. I'm going to factor out the f, and I'll get f has to be less than equal to mg over, this time it's sine theta minus mu cosine theta. So there are my two answers, and I think we need to take a good look at talking about these on Monday. Bye-bye.